This is the mark. This is okay. So yesterday we did this question, right? Now let us go ahead. Let's do more questions. So I hope everybody understood till here, right? Let's go ahead. Find the electric field due to a finite rod at the perpendicular bisector. So at this point we want to find out the electric field, right? So there's a positively charged rod, and this entire thing is a positively charged rod, and we have to find it at the perpendicular bisector. Means it divides it into exactly two halves, right? So it will have two directions of electric field at this point. One is here and one is downward. So let's call it EH and let's call it EK, right? And we know the value of EH, how much it is. In the horizontal direction it is, we'll call this E vertical, EV. That's E horizontal, this E vertical, right? And horizontal electric field, what is the formula? We had found out in the last class. Here, horizontal is K lambda by L into sine beta. K lambda by L into sine beta. And downwards will be K lambda by L into 1 minus cos beta. Right, so we got both horizontal and vertical. Right. So that is because of the blue part. Now electric field will also be because of the red part. So because of the red part, where it will be? It will be in this direction and be in that direction, right? And this will also be EH and this will be EV, right? So if you want to have a look at this, is it fine? So what will happen to the vertical fields? EV and EV will get cancelled, and horizontal direction it will add up, and we'll get 2EH. Okay, and that's equal to 2K lambda by L into sine beta. Right? And verticals will get cancelled. So that's the formula for electric field due to a finite rod at the perpendicular bisector. What do you mean by perpendicular bisector? It is perpendicular and it is breaking the rod into how many parts? Into two equal parts. Let's go ahead. A wire is bent in the form of a rectangular pentagon of edge A. Total charge Q is distributed over it. Find the electric field at the center of the pentagon. Basically, you have a pentagon and you want to find electric field at the center, right? Due to this entire pentagon and it's of side A, and total charge is distributed on it. So because of this part, electric field will be at the center. Okay, 1 second, we'll come back to this. Let's first do this part. Oh, fine. Let's complete this. So because of this part, where will be the electric field? At the center. It will be in this direction, right? Because we know that electric field due to this part is how much? You see, it is 2k lambda by L into sine beta, and it is in which direction? For this rod, you have to draw a perpendicular, right? And it is along the perpendicular. The electric field is along the perpendicular, right? So similarly, here also I drew a line because of this part where the electric field will be. I've drawn a perpendicular, and it will be at the center away from here in this direction. And why it will be away? Because it is what charge? Positive charge. They're not mentioned, nothing mentioned. I'll take it as positive. Now, what about this point? At this point, electric field will be this direction. At this point, in this direction. At this point, in this direction. And lastly, at this point, in this direction. So what will happen to all the electric fields? Now if you recall, these all electric fields will be equal in magnitude, right? These all electric field will be equal in magnitude. So if all the electric fields are equal in magnitude, all electric fields are equal in magnitude and the angles are also equal, then we know that net electric field will be how much? It becomes 0. Right? Now an infinitely long thread has a uniform charge distribution along the length with linear charge density lambda. The thread is bent into the shape as shown. Determine the electric field at point O. So what will be the electric field at point O? Let's see that. So for that, we will take a green rod like this, and it goes to infinity, right? So what will be the electric field due to the green rod at this point? You know, one will be in this direction and will be in this direction, right? And what are the values? It is, what sort of rod it is? It is semi-infinite, right? So semi-infinite rod, what was the electric field if you remember that this is a semi-infinite rod, let's say. So at this point we found out the electric field, and at this point we found out the electric field and came out to be E and E. And what was the value of E? K lambda by L, where L was this distance, right? So the electric field will be same E, or let's call it E naught, E naught and E naught. And similarly with this, because of this, it will be E naught and E naught. So what will be the net electric field at point O? Will be how much? Due to the red and the green portion, what will be the electric field at point O due to the red and the green portion? So that you can see will easily get cancelled. E naught, E naught, E naught and E naught will get cancelled, right? Making net electric field 0 due to the green and the red portion. But now we are left with the semicircular portion. This one. Semicircular portion. Because of that, what will be the electric fields? Because of that, the electric field will be along the angle bisector, as we have seen before. And here the formula comes out to be 2k lambda by r into sine of theta by 2. So that was the formula, right? You can check it. Due to semicircular rod, we have done it before. Here it is. This is the formula, 2k lambda upon r into sine of theta by 2, right? Same formula we're getting here also, 2k lambda by r into sine of theta by 2. And we can simply just simplify it, 2k lambda we can put the values. It will be 2 divided by 4 pi epsilon naught into lambda upon r into sine of, what is theta? Theta is this total angle, right? This total angle is theta. Theta is equal to pi by 2. So that will become pi by 2 by 2, which is sine pi by 4. And that is lambda divided by 2 pi epsilon naught r into 1 by root 2. So which option it is? This is. Let's go ahead. Now let us do this. EFI due to a part of a rod. So it is that is so EFI due to part of a rod. So what will be electric field due to a part of rod? Let's find out. So you can take this as a formula. What will be the electric field due to this part of the rod at this point? So this is how you find out. And let us see how it is derived, right? So let's try to find out how it is derived. For that, For that, what I'll do is, you have to prove these results you have to prove. So how do you prove this result? Let's see. So let us say this positive charge rod, and below it is, there's no rod, right? So no rod can be assumed to be made up of what? No rod means zero charge. That can be assumed to be made up of what? We can assume it to be made up of plus charge and minus charge, right? So together plus and minus will make it neutral, right? That means no charge, and that's what we wanted. We wanted no charge. Got it? We wanted no charge, and there is no charge here. So let us find out the electric field due to this. Now first let us find out due to the blue charge, the red charge. It will be in this direction, and what is the formula? If you remember, it was k lambda by b, which is this distance, into sine of. So what is the angle made by the blue charge? You see, angle made by the blue charge is this beta 2, sine of beta. Got it? And in the downward direction, it will be how much? Same, k lambda by b, but instead of sine, it will be cos of 1 minus, sorry, into 1 minus cos beta 2. And now let's talk about the red part, which is a negative charge, and the electric field will be in the x direction towards it. How much it will be? K lambda by b into sine of beta 1. This angle is beta 1, right? And since it's a negative charge, electric field will be upward due to it. And how much it will be? K lambda by b into 1 minus cos beta 1. Right? So how much is left in this direction? In this direction, how much is left? You have k lambda by b into s2. Let s2 be sine of beta 2, right? And s1 be sine of beta 1, and c2 be cos of beta 2, c1 be cos of beta 1. So in this direction, it will be how much? K lambda by b into s2, and in the negative direction, so it will be minus s2. And that is exactly what the formula we have here, s2 minus s2. And in the vertical direction, what will be the electric field in the downward direction? Let's find that out. It will be k lambda by b into 1 minus c2 is downward, minus 1 minus c1. That will be k lambda by b into 1 minus c2 minus 1 plus c1, and that is c1 minus c2, which will be break this down. Now let's go ahead. Find the electric field due to this circular sheet disk. So let us see what will be the electric field due to this circular sheet. So the formula is sigma by 2 epsilon naught into 1 minus cos theta. So let us derive how the formula we get because of a sheet. So this is basically a disk and it has got some positive charge on it, and we have to find out the electric field at this point due to the disk, right? So let's first derive the formula, then we'll go ahead. So for that we'll have to do the construction, right? And it will be a lengthy derivation. So let us begin with that. Let's say this is the disk, and big disk, right? And because of that, we have to find out the electric field there on the axis of it, right? Okay, now nice. So something like that, right? And because of this disk, I want to find out the electric field. So that is the entire uh, process, right? I'll write down here. Find electric field due to the disk on axis, right? So let's see how to do that. So for that, we know disk is made up of. So let us write this. Disk is made up of concentric rings, right? So we can write down that note. Right. So my point is this, that this disk is made up of rings. Like there'll be one ring here, one ring here, right? So all these rings together make up this disk, right? That's my point. So I hope all of you all understand that part. Okay. So what we're going to do is, we don't know how to find out the electric field due to the disk, right? So what we'll do is, we'll assume that the disk is made up of small rings, and we'll find out the electric field due to one ring and integrate it. That's the process, right? Just find electric field due to one ring, find it out there, and integrate it. So we'll catch hold of one of them like this, make it smaller. How many are there? Right now, too many. Okay, yes. So we got hold of one of them, and now we will reduce its size, right, and we'll put it here. Perfect. It sits absolutely concentrically. Nice. And then let's make it dotted. Right, and we'll get another, and we'll make it even smaller. Okay. And then we'll put it here, and this one, put it here, and we'll make it smaller, a bit smaller, then put it like this. Nice. Right. So what we have to do, you see, I told you the disk is made up of small rings, right? So this is one of those rings. This is one of those rings, right? This is one of the rings. And because of this ring, I'm going to find out the electric field at this point, right? That will be small electric field dE. That will be, what is the formula? K. So because of the ring, what was the formula? Let's check the formula because I don't remember it. We had derived somewhere here. Let's use the formula. Here it is. So kx q naught divided by x square plus a square whole to the power 3 by 2. Kx q naught. Kx q. Kx q naught. Kx q naught divided by x square plus uh, y square to the power 3 by 2. Where what is dq, guys? Dq is the small charge of this ring. The charge is dq, right? And the radius of this ring is, let's say, x. Right? The radius is not x. Let's call it y is the radius, and x is this distance. X is this distance. That vertical distance is y, and this is the small electric field due to that small part of the ring, right? So I have put a clear till here. That is a small electric field. So this is a small electric field. To find out total electric field, what we'll have to do? We know this disk is made up of small rings, right? So this is the electric field due to a small ring. So if you want to find out total electric field, of course you'll have to go and integrate it, right? You just integrate it, you will get the total electric field at this point due to the entire disk, right? And let's see how to do that. And let's call this distance as h. So this y, this is x, and that's h, right? And of course this 90 degree. Right? Now I know there's something called sigma, which is charge per unit area, and sigma is dq divided by, dq is a small charge on this, divided by area, which is 2 pi y. Okay, what will be the I can write sigma is charge per unit area, means it is this dq, whatever charge is there on this, which is dq, divided by dA. What is dA? dA is whatever the area this has, that area is called dA, and the ratio is called dq by dA, which is sigma, which is the charge per unit area, right? Right? Now what will dq be equal to? dq by dA we have written, so let's find out dA first. dA means differential area. So how can we get this area? This dA, how do we get the area of this ring? What we can do? For that, we can cut it from here, right? And we can spread this entire ring. So how will it look like if we spread the entire ring? It will take the shape of a, if you spread this entire ring, it will take the shape of a rectangle, right? Like this. You know? So basically what I've done is I've taken this ring and I've spread it over. So, and let's say the area of this is dA. So can you tell me what will be the length? How much will be the length of this? How much? It will be, length is 2 pi r. So it will be 2 pi r. 2 pi r. And r is the radius, means y is the radius. So 2 pi y. That's the length. And what is the thickness? This thickness is dy, right? This thickness is dy. Why it is dy? If you're wondering, see. Y is here to here, right? So what will be this thickness? A small change in y. Right? So this will be, this part will be how much? Would it be dy? Right? That is what I said. This small part will be dy. Now you can write dA easily. You can write the area easily. So this 2 pi y is the length and dy is the thickness. So what will be the area? Small area. dA will be how much? It will be 2 pi y, which is the length, into the thickness, which is dy. So 2 pi y dy will be the differential area. So that will be 2 pi y into dy. Correct. So that is the differential area, and now there's a lot to go about this. So we'll do the rest of the derivation in the next class. I'll save this page. We'll do it in the next class. Save as in the desktop document 12th JEE. It will be C 12th JEE physics. It will be 12 space. Today date is 13. Save it as 13. Save. And then let's save this also. How much you've done today? You've done this we have to do, right? Uh, all selected. Then this, this, and topic is electric field due to electric field due to rod and disc. So that's the heading.